Welcome DIKWP, 小工 aboard. Your learning journey starts now. Ever wonder how much you can actually learn in your entire life? Is it infinite? Or is there a cosmic limit? Forget philosophy for a second. Let's talk physics and bits. We're diving into the hard limits of human learning using something called DIKWP data, information, knowledge, wisdom, purpose. Buckle up. We're estimating the total DIKWP you can cram into your head. Alright, first stop, the universe's rulebook. Landauer's principle says erasing one bit of information costs, at least, 10 to the power of negative 21 joules. Sounds tiny, right? But here's the kicker. Our brains are incredibly inefficient compared to this theoretical minimum. They use about 10 to the power of 12 10 to the power of 13 bit per joule. Why? Noise, errors, maintaining ion gradients, all that jazz. With a brain power budget of around 20 watts, we process roughly 10 to the power of 14 bit per second. So, while Landauer gives us a hard floor, the real ceiling for what we can do is way lower, dictated by biology, not just physics. This gap is huge, 10 to the power of 72, 10 to the power of 8 times. It means most energy isn't directly used for learning new stuff. It's just keeping the lights on in our biological computer. So, how do we measure this lifetime learning? Not just one way, we need two metrics. First, cumulative flux L. Think of it as the total amount of stuff you've ever tried to learn or write down in your life. It's the throughput. Second, maintainable stock S. This is the real deal. How much of that stuff can you actually pull up and use right now, after accounting for forgetting and needing to rewrite things? This is what matters for purpose P. Now, how do we estimate these? We use a neat formula derived from a simple model: writing, forgetting, rewriting. The key parameters are EOP, the energy cost per effective update, and lambda, the forgetting rate. The total maintainable area A over your lifetime is bounded by your total energy E divided by this product. A is less than or equal to E divided by open parenthesis EOP times lambda close parenthesis. More energy, less forgetting, or cheaper updates mean you can hold on to more knowledge long term. Okay, we've got physical bits, but learning isn't just about raw data. It's about meaning, semantics, and hitting your goals. That's where DIKWP comes back in. We introduce kappa sub DIKWP, which combines semantic compression rate, eta sub sem, and purpose alignment x sub align. Think of kappa as a measure of how much redundancy and deviation there is. A smaller kappa means more efficient, more aligned processing. So, the effective DIKWP content h sub f is just the physical bits h divided by this factor. H sub f equals h divided by kappa. Putting it all together with net retention f sub learn, we get an estimate for the total lifetime net learnable DIKWPQ sub learn. For an average human, assuming 80 years, 20 watts brain power, typical efficiencies, and maybe 50% retention, we land somewhere in the ballpark of 10 to the power of 21 plus or minus DIKWP bits. That's a lot of meaningful stuff. Finally, let's talk about that feeling of infinite context from AI models. When does a model seem to know everything? Psychologically, it happens when its available context massively exceeds what you, as a human, could possibly test or verify. We call this the subjective infinite context threshold. The required DIKWP for this illusion is roughly gamma times Q human test, where gamma is a safety multiple, maybe 10 to 100. Translating this back to tokens, considering model specifics, we find that to create this feeling of infinity for an average human, The model needs to have access to about 0.4 million to 1.5 million tokens. In terms of DIKWP bits, that's around 10 to the power of 8 to 5 times 10 to the power of 8. So, the big takeaway: the absolute limits of human learning are finite, governed by energy, forgetting, and semantic efficiency. But perception is powerful. A sufficiently large and well-aligned system can make us feel like we're tapping into something truly boundless. Fascinating, isn't it?